All right. Check it out. Last Monday, huh? We stoked? Glad to see some of you here that maybe don't come here very often. Welcome. Anyway, so Sunday, I think it was Sunday, yesterday, I bombarded you with a lot of announcements, I think. Okay. One was, did I put up? No. I did put up extra credit opportunity. All right. That's filling out your student evaluations. If you go on D2L, there's a link out there that drags you just to this class, and you can talk all the shit you want about me. Okay. I don't know it's you, and I won't know until after I grade the exams and upload all your final grades. So be honest. I'm all ears, or I will be. And if I'm not, Craig Woolard, who's the department head, will make me think about this. So be honest. Please fill them out. The other item is homework, right? I assigned another homework assignment. It's going to be due next Friday, similar to one that was due last Friday. Quiz, very similar to last weekend's quiz, which is actually due the end of today because a number of you had some issues with accessing the quiz. So that's probably why some of you have a 0 grade out on the quiz, even though you already took it. It should update at the end of the day today, okay? So quiz will be available this Thursday through Sunday. It'll be over pressure vessels and combined loading. Same with the homework as well, which is already out there. So feel free to get started on that. I made the exam, okay, over the weekend. 35 multiple choice questions, and then one large question. It has about 8 sub questions to it. Okay, it's a combined loading problem. Okay. All right. You can bring in all of the 0 notes. So essentially, the appendix in the text that's out on all the notes that are labeled as 0, 0, 0, 0, 0, 0, and I think there's one more, 0, 0, 0, 0. Okay, out on the D2L, which is like your overall equation sheet that's actually in the appendix on the text. It's like basically all the pertinent equations from every chapter in the book. You can bring that in. You can bring in an 8.5 by 11 sheet of paper, whatever the hell you want to write on it, you write on it, okay? Small, big, whatever. You just get one sheet of it. The other, yes,
Does that have
Monica?
to be handwritten?
Yes, I'm going to make sure of that. Yep, thank you for clarifying. The next is the properties, geometric properties of areas, right? Talking about moment of inertia, section modulus, stuff like that. Another note, another one of those 2 notes sheets that you can print off of D2L is talking about deflections, right? Slopes of beams, kind of what we use when we do superposition, right? We use simplified problems, and then we add those simplified ones together, similar to what you had in the homework. Add them together to get a solution for something that's, say, combining 2 different, simpler problems together. You can bring those as well. Any other questions? Yeah?
We're taking it all at once, or is it multiple choice like at a different time?
All at once. All at once. Yep. So noon in this room. We'll be in here from noon to 2 o'clock. Well, 1:50, I guess, is when they're supposed to boot you out of here. Okay. And I'm assuming because it's finals week, there will be a line of people outside waiting. So I will need to, unfortunately, stop. So, okay. All right. Sweet. Don't look so excited. Okay. We have, maybe something exciting. You have 2 more visits with me this week, right? Wednesday and Friday. We will definitely get done with this material by the end of day Wednesday. Friday, I'm planning on just being here to answer any questions. We can go over kind of a review, some of the things that you should be thinking about as we go through, or you guys start to study for the exam. Okay? All right. So, the last part of this class, as I mentioned on Friday, is combined loading, right? That's where we take all of the concepts that we've learned in this class, right? Axial loading, torsional loading, pressure, bending, all of those things, and we look at cases that incorporate all of those load sources, into individual problems, right? So I gave some analysis methods, kind of broke it down into really two big categories. One is when we look at beams, we're going to have a distinct approach, right? We're going to want to find our reactions, draw a free body diagram, right? Find our reactions. From those reactions, then we can start developing what are our shear and moment diagrams. We're really going to be looking like we have started in our example. We're looking for the stresses at a specific location, right? Not only along the span of a beam, but also within the depth. Because as we know with bending stress, right? My over I, negative My over I, it matters whether we are sitting at the centroid of our cross section or if we're at the top of the beam or the bottom of the beam, right? And similarly with shear, same thing, right? Based on where we are at in the cross section, it's going to change our Q, right? First moment of the area, Y times A, Y bar times A. So we need to know not only where we are in the depth of the cross section, but also where we are along the length, right? Because the shear and moment can change as we go along the length. So we want to find a reaction so we can find what our demands are along the length of our member, more specifically, where we are trying to figure out what the stresses are. Then we can calculate stresses on the block, on a stress block, right, based on those loads in the geometry of our beam. And then we can finally go to Moore's circle, because we are always looking for the worst case stresses at a given location. And so we need to utilize Moore's circle at times to make sure that we capture our principal stresses, right, which is our stresses in which we would have zero shear stress, our extremes, right? And then we can use that Moore's circle to also figure out our extreme shear stresses also, right? Our max shear stresses. So that's our beams approach. For other members, right, things can get fairly complicated fairly quickly, right? We can have bending in two directions. We can have axial load. We can have torque, okay? So when we have those things, when we approach other members, which we're going to start an example today, we're going to look at a free body diagram, but we're going to do that free body diagram twice. And what does that mean? Well, we're going to break our force systems into two separate ones that incorporate our forces and our moments, right? We're going to have a shear force, we're going to have an axial force, right? And sometimes, based on the configuration, those shear forces and axial forces, say, over here, right, in some bending problem or some mechanism, is going to create a bending moment or torque or something else happening where we're actually looking for, right, in our mechanism. And so separating them can make things a bit more simpler and isolate the forces and the moments. So then after we do that, we can then figure out a stress block for each of those two force systems, right? Determine all stresses due forces and moments, right? Pressure if it's present. And then once we have these two essentially stress blocks, right, we can add everything together using superposition, because we know those forces and moments are acting together. We just separate them to make things a little bit simpler. And then again, once we have that final superimposed stress block, we can figure out Moore's circle for that stress block and then figure out our maximum stresses, right? Our normal stresses, which are our principal stresses, and our shear stresses, which are the top and bottom of our circle. So when we started our example, right, we started our beam example on Friday, and they asked us to determine the stress states at point H and K. And as I mentioned on Friday, right, us as engineers, you as engineers, would be the ones deciding where we want to look at this beam, right? What points H and K are and where they are on our beam. Okay? In this instance, they gave it to us. I will give it to you in the exam. That's not, I'm just saying in the future, right? As you do this more and more, you will find that you are the one that's going to decide where you look at this member. In this case, they gave us H and K. As we know from our approach, right? We need to figure out our reactions and our shear and moment diagrams, so we did that. Now that we know our shear and moment diagrams, more importantly, we know our shear and moment as it relates to our 2 points of interest, right? H and K. Because we know our demands at H and K. We could draw a free body diagram, which helps us discern what we have and what we don't have for our positions at H and K. In this case, right, we have our design demands, moments and shears. But we know because we have moment and shear at our 2 points, we're going to have shear stress and normal stress. And we know that the equations for shear stress and normal stress are shown there, right? We have negative my over I and VQ over IT. And so we need to figure out some more of our parameters. So we did, right? We're gonna have a Y dimension, and we know from going through bending and flexure that our Y dimension is measured positive upward from our centroid, right? So if we're above our centroid, Y is positive. If our point of interest is below, it's negative. That's why for H it's negative, and for K it's positive. We also know for negative my over I, well, we need the moment of inertia. And so I decided, as I explained on Friday, I just did the overall rectangle minus two smaller rectangles. And you could go through the parallel axis theorem. Totally valid. Totally valid. Okay. So I figured out the moment of inertia, and we figured out, based on now knowing the moment y, right, the distance to our point from the neutral axis or the centroid, and our moment of inertia, we could figure out our stresses. We figured out our stresses. Our stress at H is 26.8 megapascals positive, so it's in tension. And our stress at point K is 66.61 megapascals in compression, right, because it's negative. Now we need to figure out our shear stress, right, tau, VQ over IT. We know Q, first moment of our area, or the integral of I dA, right, is just essentially the summation of all of the parts of our shape above or away from our point of interest, right, of y bar A, right? Our centroid of our piece times the area. Whoops, well, in our case, for this, right, so if we were looking at H, y bar A, we would summation. I'd probably look at three rectangles, right? Y bar A means what is the y bar or distance to the centroid of this rectangle times its area, plus the distance to the centroid of this rectangle times its area, plus this one as well, right? So if you do that, and you can do this any way you want, right? You could separate this into so many different rectangles, right? You could look at just the flange and then cut this off above the flange and just look at the web, right? You could cut the web into two rectangles and do it twice. Doesn't matter, right? You're always going to come up with the same answer, but we're looking for the distance to the centroid, or y bar. Whoops, not that. All the way up to the centroid. Y bar times area, right? We do that for each of our rectangles. For the area that's beyond our point of interest, right? We cut it horizontally at our point of interest at H, as we did when we learned about shear stresses. So if we do that, I'm not going to bore you with all of the details. We get 642,652 millimeters cubed, right? Y is in millimeters, A is in millimeters squared. We get millimeters cubed. Well, based on that, we've got all the other parameters, right? V, we know from our shear diagram. Q, we just calculated. I, we calculated to figure out our bending stress. And then T is the width of the cross section when we cut that horizontal plane, right? So if we can imagine at H, we are going to essentially cut this member right at H. And we want to know how much of this member is along this cut plane, right? How long is this? Well, so that would be our thickness T, or T. So T is 9 millimeters. In the homeworks, I think you had two webs, right? So if we had another web coming down here or another web coming down here, it'd be 3 times 9 millimeters, right? Because we're cutting 3 sections. In this case, we only have one, so our thickness is 9 millimeters. So, based on our shear diagram, the shear at point H we determined was 115 kilonewtons. We have 652 millimeters cubed. I'm going to get to newtons, because we know a megapascal, right, is a newton per millimeter squared divided by I 202.7 times 10 to the 6th. That's millimeters to the 4th. And then I said just a second ago, our thickness, right, or the width of our cross section that gets cut by that horizontal plane is 9 millimeters. So I put that in there. And we get tau at point H equal to 40.5 megapascals, right? Same exercise at point K, VQ over IT Q now equals, 622,852 millimeters to the third. What does that mean? Well, again, we're going to cut our cross section at our point of interest, and we're trying to figure out what's the first moment of the area about the cross section that's beyond our horizontal cut, right, which is at our point of interest. So again, we could break this thing up. I might do one rectangle there and one rectangle there, and we would essentially say, okay, well, we've got Y bar, and this thing has some area. This has another Y bar, and it has another area, right? We would take our Y bars times our area, sum them all up, and that would get our Q. And that Q would be what I calculated here, hopefully, 622,852 millimeters to the third. So if we run through the entire calculation, we have 45 kilonewtons. That was from our diagram up above. Our Q we just calculated. I'm going to convert to newtons. Again, 9 millimeters. We're still cutting through the web. So now we get 15.4 megapascals. Okay. Last part of this, I believe they asked us for determine the stress state. So we're going to finalize our calculations with giving a depiction of what is the stress state at our 2 points, right? So we're going to create our two little blocks. We look at it, right? We've got our little block here. So we're going to make a block at H. We're going to make a block at K. And we're going to figure out what are the normal stresses. And shear stresses. Yeah. Oh, got a holler. What's up?
So at point K on our shear and moment diagram, our V was negative 45 kilonewtons. Would that make our tau H negative then?
No. What it does is it gives you a direction. So because our shear was negative 45, when we draw a free body diagram of K, it depicts that our shear is down, right? Because a positive shear is, if you guys remember, positive shear, up on the left, down on the right. That's our sign convention for shear, positive shear. Whoops, not tau, what am I doing here? Positive shear, right? And so it depicts that our shear direction on this face is downward. And so on this face here, it's downward, right? This is point K. On point H, if we go back up here, right? We had a positive shear at point H of 115 kilonewtons. That means our shear on that cross section is downward on the right hand side, which is positive, right? Up on the left hand side, down on the right hand side. So our shear does something like this. Because it does something like this, we all know it does something like this. To maintain equilibrium, right? Can't have this thing flying off into space. We also know that we don't have any overall axial forces in this beam, just bending forces in this beam. And we know that there's bending forces that created bending stresses. And we know if we drew a little square at point H, we have a tensile stress acting of 26.8 megapascals. So that means on our X face, we've got this 26.8 megapascal force, right? Or stress that's acting, stress, not force. Our tau is 40.5 megapascals. We got no stress on the top surface of this stress ball, right? There's nothing trying to squeeze this beam vertically. So that's our stress state at point H. At point K, again, as we mentioned, we figured out our direction of our tau based on the free body diagram. We know our shear stress tau is 15.4 megapascals, we just calculated. We also know that we have a compressive stress. It's in the top of the beam under positive bending. So we know it's going to be in compression. Our sign convention told us that. So we have 66.61 megapascals. Again, we have no forces in the vertical direction, so there's no stresses on the vertical faces or the top and bottom faces of our block. And that would be the stress state. This was a question on the exam, right? I could ask you from here. I could ask you, what is the principal stresses at point H? Or what is the maximum shear stress possible at point H or point K? And in that case, right, we would continue by plotting our Morse circle for each of our stress states. So we've got our sigma and our tau. We would plot our 2 points. So if we looked at point H, for instance, right, we have tension stress on the X face with a shear stress of 40.5 in the clockwise direction. Clockwise is above the x-axis, so we know we're somewhere in here plotting this point. Okay, so we're going to plot a point out there. Say it's right there, right? This is our sigma x comma tau xy, right? That would be 26.8 comma 40.5. And then similarly on the y face, we need to plot another point, as we know from Morse circle. In that case, we do not have a normal stress, so we're going to be on our y-axis. We know the shear stress is acting in the other direction. It's counterclockwise. For counterclockwise, we're down here below the x-axis. So we're going to be on the y-axis, down here an equal distance below the x-axis from our other point. Right? This is sigma y comma tau y x. Y face at x direction. We would then draw a circle. Something like that, right? And from there, we could figure out our radius. We could figure out our center. Right? We could figure out our radius, what our center is, what its x and y is, right? Y being 0. Knowing the center and the radius, we can figure out our principal stresses, right? These are our extreme magnitudes, or our normal stresses that don't have shear stresses, and our stress state. And then similarly, because we know the radius, that's our maximum shear stress, right? Tau max, sigma 1, sigma 2. And we could do the exact same thing for whoops. I need to turn on the cheat button here. Something like that, right? We could do the exact same thing with the stress state at K. Then I could ask you a step further in the exam, and I could say, all right, if you had a material and the yield stress was 36 KSI and you wanted a factor of safety of 3 with respect to design, does this material work or not work at point H? Right? So if you went, you said, okay, 36 KSI for yield, right? For normal stress, you divide it by your factor of safety, you get an allowable stress, and you could relate that to what your maximum stress is, right? Sigma 1 or sigma 2. You could say yes or no. I could also ask if there was a weld at an angle or some sort of connection, and I asked you what was the stresses at a 30-degree angle at point H. You could figure that out too, right? Knowing that Mohr's circle is twice that of real world, so you'd rotate whichever direction, 60 degrees, in order to figure out what the stress state was at 30 degrees. Got a whole semester worth of stuff. Okay. We've got one more example. Well, two more examples. So that was our beam example. Fairly straightforward. I think for the most part, we've done most of that, right? Through some of the other homeworks and some of the other parts of the text. Now when we're looking at other systems where we have force systems, right, that are going to create not only, or are going to have not only forces, but create moments. This is where it's helpful to split the system up into two components, right? All of our forces that are acting at a point and all of our moments that are acting at a point. All right, so this is our example of other cases, right? So again, we're trying to figure out what are the stresses at point H and K of this pipe with an elbow, right? Hanged fixed at a wall, and it has these two forces on it: 9 kilonewton force that's acting downward, a 13 kilonewton force that's acting off to the side or along the x-axis here, right? We've got coordinates here of x, y, and z. So 9 kilonewtons is acting in the y direction, our 13 kilonewtons is acting in the x direction. Our H and K, they give us, right, where H and K is in relationship to our two forces. You see that's going to help us. They give us where our forces are in relationship to the pipe, right, that's coming out of the wall, that's fixed from the wall. So as mentioned, when we start looking at other cases, it makes sense to separate our systems into two force systems. One is the forces at the location of interest. And the other one is, what are the moments at our location of interest? Okay. So if we look at essentially a cross section at points H and K, right, 1.2 meters back, 0.65 meters up from our applied forces, and 1.2 meters back from our applied forces, we cut the section. And we say, okay, well, what are the forces acting at that cross section, right here? Any ideas of what the forces are? What are the forces that are going to be acting at H and K at this cross section, right?
Kilonewtons in the X and then 9 kilonewtons in the Y.
Yeah, right? So we're going to be moving our forces. This 13 kilonewton force that's acting in the X direction is always going to be acting in the X direction, even way back there at the point of fixity, right? That's statics, okay? So we're going to move our force back to our X direction. So we got 13 kilonewtons. It's going to be acting in the X direction. Still going to be acting in the X direction at our point, H and K. And then also, we're going to have our 9 kilonewton force, right? It's acting downward. Well, if we were sitting there holding this pipe at the wall, we would still feel 9.9 kilonewtons downward, right? Someone puts 9 kilonewtons down there, I'm going to feel 9 kilonewtons right here. Statics, some of the forces in the Y have to equal 0. But when we jump to moments, right? Our moments, which can be both moments about X and Y, but also a moment about Z, which is the same thing as a torque. Torque, moment, couple, all the same thing, right? It's just a force of a rotation about an axis, right? Force about an axis. And so if we take those two forces, right? As we know, when we move forces, those forces come with them not only the initial force, but the moment that's applied due to that force, right? So now if we're holding on to this pipe on the wall and someone pushes down at 9 kilonewtons, what's that going to do at H and K? Right? What's it going to do at H and K? Yeah.
So you're going to have that force of like that 9 kilonewtons being transferred over the 1.2 meters.
Exactly, right? And what axis is that going to try and bend about?
So that's going to try to bend it off your Z axis. So it should be going downwards in the Y.
So if we have 9 kilonewtons, right? Holding this pipe, someone pushes it down at 9 kilonewtons, right? We got this x-axis that's sitting here, right? That 9 kilonewtons acting in a moment arm of 1.2 meters is going to want to bend about, right? The x-axis. Right? So we've got, now if we look at our cross section here, that 9 kilonewtons is going to create double vector arrow signifies a moment, right? It's going to be about the x-axis. 9 kilonewtons, right? We're rotating about the x-axis here. 9 kilonewtons times 1.2 meters. We got 9 kilonewtons times 1.2 meters. 10.8 kilonewton meters. Right? So now we have the 13 kilonewtons. Well, I guess first off, is there any other axis with which the 9 kilonewtons is going to force a rotation about? Yeah.
I have a question.
Yeah.
Why is the 9 kilonewtons in the direction of the X? Like,
Because that's the, if you look at the right-hand rule, right? So you got your moment arm and you got your force. If you curl your fingers in the direction of the force, your thumb's
Yeah.
kicking off along the x-axis.
Yeah.
Is there any other axis that the 9 kilonewtons is going to rotate about? No? Yeah. So now we have our 13 kilonewtons. So again, if we look at the right-hand rule, we are at 13 kilonewtons. If we curl in the direction of the force, right, this thing's going to be creating a moment about the y-axis. But also, isn't it going to be creating a torque, right? A moment about the z-axis also. So it's not only trying to bend the pipe, but it's trying to twist the pipe also. Everyone see that? So if we're trying to bend the pipe, We're bending about the y-axis now, right? 13 kilonewtons. Well, it has the same moment arm as our 9 kilonewtons at the 1.2 meters. Double vector arrow, we've got 13 kilonewtons, moment arm 1.2 meters. We get 15.6 kilonewton meters. Acting upward, right? Right hand rule, 13 kilonewtons. It's going to be acting up, my thumb's up. That's in the direction of the y-axis. Yeah.
Would it be the 0.65 for that arm for 13 kilonewtons?
In the z-axis, yes, which is in and out of the page. That's this one, right?
Okay.
Because if I curled my fingers in the direction that this is rotating about the z-axis, I'm going to be, my thumb's pointing outward, so it's going to be positive about the z-axis, but it's going to be rotating about the z-axis. So we got 0.65 times 13 kilonewtons. That's this one out here, 13 times 0.65. We get 8.45 kilonewton meters. So this is why the method for other systems, right, it can get pretty complicated pretty fast. We're moving this force all around a system and looking at a specific point that might be quite a ways away from our applied forces. But you need to transfer those applied forces and figure out what are the applied forces at the location of interest. So to simplify things, we just try and break it up, right? We look at what are the forces applied at that location. Well, we're still going to have our 9 kilonewtons. Right? I still got to hold up my pipe with 9 kilonewtons. And if someone's pushing it off to the side, I'm still going to have to resist that pushing off to the side with the same amount of force. And so we have our forces, and then we also have our moments. Because moving these forces along this system to, right, the fixed point, the resulting location, we're going to have resulting moments. It's going to be twisting it about the longitudinal axis, is going to torque the pipe that's holding in my hand. It's going to want to twist. Also is going to want to be bending in 2 directions based on the applied load. Everyone see that? So, based on torque, moment, and shear, right? That's what those forces are, essentially shear forces acting at our location of interest. We're going to have 3 different stresses. We have our shear stress. We've got our normal stress, right? That's due to moment or flexure. And then we're finally, in this case, we're going to have one more. Got to dig deep for this one. It's been a while. Right? Torsion, TC over J, right? The torque times the distance from the center divided by your polar moment of inertia, is J. Which is where the notes that are out on D2L would be worth printing off, because out there in properties of geometric shapes, we get equations for what J is, right? It's also in the notes. You put that on your note sheet. If this pipe, for instance, if this was a pipe that happened to be to move pressurized like steam, okay, for the heating plant, right? We might have, could have pressure too, right? We could have where, based on our derivations last week, we know that our stresses can come in the form of hoop stresses or longitudinal stresses. So in case we didn't, we could have both these forces applied, and we could also say that the pipe, inside the pipe, the pressure is 35 psi. Right? And if you knew the pressure was 35 psi, we know that we have hoop stresses, right? Trying to burst the pipe. And then we also have longitudinal stresses, also trying to burst the pipe. And we know hoop stresses are twice that of longitudinal stresses. And that's why whenever you freeze a garden hose or freeze fixed piping like copper pipe or steel pipe, right? That crack that usually forms is usually along the length of the pipe. That's because your hoop stresses are the greatest when it comes to pressure, right? So it's always going to be bursting in that direction, okay? Or twice as much. So now that we've broken down our system into two force systems, we have our shear forces or just our forces on our system. They could be axial forces. We could have a force acting in the z direction if we had a force acting in the z direction, but we only had forces acting in the y and the x. But we could have had a force acting in the z. So we have our force system and then we have our moment system. So we want to now look at each of our systems independently. Ultimately, we're trying to figure out what our stress states are at h and k based on these applied forces. So we can figure out a stress state. We're going to do that for both the forces and the moments, and then we can come back and add them together, right? Use superposition. So if we look at these forces, these are all shear forces, right? Forces acting perpendicular to the longitudinal axis, remember? So we have 9 kilonewtons and 13 kilonewtons. So if we have shear forces, we have shear stresses. BQ over IT is our governing equation, as we know. Out of this equation, we know now what shear is, but we need Q, I, and T. Moment of inertia of a pipe. Right, they gave us our inner radius and our or inner diameter and our outer diameter. From the notes are also out there in that note sheet that I would recommend printing off. We get this equation that relates the moment of inertia of a pipe with respect to diameters, which is this equation, right? Pi over 64, outside diameter to the fourth minus the inside diameter to the fourth. We get 31,439,850, which is probably more accurate than required. You go, right, this is Appendix A stuff here. Q,
So 37, right? It's a 7.
31. 31 million? Yeah, 31 million. 31,437,850 millimeters to the fourth. As I mentioned, that comes out of the equations in Appendix A, which are out on D2L. You're welcome to print those off and bring those to the exam. Q, first moment of the area. Well, that's 1/12 d cubed minus d cubed, big D minus little d. That's 212,352 millimeters to the third. That all comes from Appendix E. H and K. We know shear stress is maximum at the center. As we get out to the outer edges, it becomes 0, right, in the direction of the applied force. So at point H, our 9 kilonewton force applied provides 0 shear stress, right? Does that all make sense? Because if you looked at a cross section, we're looking at point H, right? Q is 0 at point H, right? If we were looking at our applied shear is in that direction. Q being Y bar times A. Well, if there's no area beyond our point of interest, then our Q is 0, Q is 0, our shear stress is 0. But if we looked at a force going the other direction, right? Our 13 kips, or kilonewtons in this case, right? Our H is going to be on the half depth, right? We're now going to be looking at Q for this entire section here. Well, now this section has a centroid and an area, so it's got a Y bar and an A. So now we have a Q value, so now we have shear stress. So based on that, if we start by saying, let's look at point H, tau in the X direction. Well, 13 kilonewtons is acting in the X direction, as I just discussed. We're going to have shear stress based on a force acting in the X direction because we're going to have a Q with point H. Well, if we know our V, which is 13 kilonewtons, Q, well, we know 212, 352 millimeters to the third. I'm going to convert to newtons again because I want megapascals when we come out of this, or newtons per millimeter squared. We have our I, 31, 439, 850 millimeters to the fourth. Our T,
Is it
well,
439 or 437? Because you said 37.
oh, this is 9, no. 31, 439, 850 millimeters to the fourth. Yeah. T, like we did with the beams, right? We're going to effectively cut our cross section horizontally. If we're looking at shear going this way, we're going to cut it horizontally, and we're going to look at the width of our cross section with which that horizontal plane cuts through. In this case, it's going to be 2 times the thickness of our pipe, which is essentially the outside diameter minus the inside diameter. So we have 200 minus 176 millimeters. We get a tau in the X direction of 3.66 megapascals. Tau Y, tau Q equals 0. Therefore, tau Y equals 0, right, as we just discussed. And if we go through K, tau Y, well, we'll just go tau X, right? We know tau X is 0 at point K. This is point K over here. Because when we have a force in the X direction, like we show here, our Q is 0, right? Our Q is 0, Q is 0, then our shear stress is 0. And we will finish tau Y on Wednesday and finish this exam. Don't forget, if you weren't able to access the quiz, I did open it till midnight tonight. Please get out there, finish that.